Hello, and welcome to our session on encoders in digital logic circuits. An encoder converts a series of 2 to the power n inputs to a binary equivalent of n bits at the output. In this example here, shown on this first slide, n is equal to 2. So there are 2 to the 2 inputs, or 4 inputs, and 2 outputs to this encoder. And what the encoder does is it converts those inputs to a set of outputs that indicate where the single 1 in the inputs occurs. So for example, when a 1 occurs in the least significant bit position at Y0, the output indicates that by setting A1 and A0 equal to 0, 0. When Y1 is equal to 1, then the output is encoded as 0, 1. When Y2 is equal to 1, the output is encoded as Y0. And finally, when the most significant bit, Y3, is equal to 1, that's encoded at the output as 1, 1. Implementing the basic encoder is straightforward. We can see here that A1 is simply equal to the OR of Y3 and Y2, and A0 is equal to the OR of Y1 and Y3. And this can be implemented simply using two input OR gates. The one for A1 contains inputs Y3 and Y2, and the one that produces A0 contains inputs Y1 and Y3. We can also implement using the more space and power efficient NAND gates and inverters rather than an OR gate by recognizing from De Morgan's theorem that an OR gate with its inputs inverted is equivalent to a NAND gate. So we can use that information from De Morgan's theorem to implement the output bits of our basic encoder A1 and A0 using NAND gates and inverters. And to do that, we'll just invert the inputs to the OR gate that we used in the previous slide and instead use a NAND gate to produce the outputs A1 and A0. So in this way, we can implement this using NAND gates and inverters. And in the previous slide, we had 2 OR gates, and here we have 2 NAND gates and 4 inverters. And this implements the basic encoder for a 4 to 2 encoder. A more complex version of the encoder is the priority encoder. And what it does is it also takes 2 to the n inputs, here shown as 2 to the n equal to 2 squared, or 4 inputs, to n outputs, or 2 outputs in this example, but it does so by allowing for a few more different cases than the basic encoder. It allows for all of the inputs to be 0, in which case the valid signal indicates by being a 0 that the input is invalid. In other words, there's no priority, and the outputs A1 and A0 become don't cares or irrelevant in that case. In the other 4 scenarios, the output will encode the value of the input, which input contains a 1. And when in cases when there's more than one input that contains a 1, that input that has the highest weight will dictate the code at the output. For example, when the highest value or the most significant value of 1 occurs at the Y1 bit, that's encoded as 0, 1. And the value of Y0 becomes irrelevant. When Y0 is 1, on the other hand, that'll be encoded as 0, 0. In both cases, the valid bit will be 1, indicating at least one bit at the inputs is equal to 1. When the most significant bit, Y3, is equal to 1, that will be encoded as 1, 1, with the valid bit again equal to 1. And finally, in the 4th line of the truth table, a value of 1 at Y2 will render any 1s at Y1 and Y0 irrelevant and will be encoded as a 1, 0 at the output with again a valid bit of 1. Now it's straightforward to implement the 4-input priority encoder for both the valid signal and the A1 and A0 for 3 total outputs. Using a product of sums, we can look at the first line in the truth table to directly come up with the expression for the valid bit, and that expression will look at the values of the inputs where the output, valid in this case, is equal to 0. And for every value that has a 0, we'll express that in its uncomplemented form. And in this first line of the truth table, all the values of the inputs are equal to 0, so they'll show up in their uncomplemented form for a valid expression equal to y3 or y2 or y1 or y0. The implementation for A1 is just a little bit more complicated and requires a Karnaugh map to find the simplified expression. When we have the Karnaugh map expressing what's going on with A1 in the truth table here, we can then see that we have 2 groups of 8 to address, and A1 is simply equal to, in the first group of 8, the single variable that does not change in A1 is equal to y2, which remains a 1, so it shows up in its uncomplemented form. And we OR that with the term that represents the second group of 8 in this Karnaugh map. And in the second group of 8, it's y3 that doesn't change values, so we express that in its uncomplemented form because y3 is equal to a 1 in all cases within this group of 8. So that gives us a value of A1 equal to y2 or y3. A0 is also pretty straightforward. Once we create the Karnaugh map from the truth table, we'll find that we have a group of 4 to work with here, and also a group of 8. Again, we'll look for values within each group that do not change value. In this case, for the first group of 8, y3 does not change variable values. It's the only variable that doesn't change value and has a value of 1, so it appears in its uncomplemented form, just as it did in the previous slide for A1. For this group of 4 here, we see that y1 does not change value. It's equal to 1 in both cases within the group, so it's expressed in its uncomplemented form. And y2 does not change value either, but it's equal to a 0, so we express it in its complemented form. And that's the final simplified expression for A0 in the priority encoder. So here we've looked at, briefly, the basic encoder, which encodes one code to another that's more compressed. And the basic encoder, just like any encoder, takes 2 to the n inputs and converts them to a compressed encode output. And the basic encoder does that assuming that only one value in each of the inputs, possible sets of inputs, is equal to 1. The priority encoder, on the other hand, accommodates the fact that more than one might occur at the inputs and encodes them appropriately according to the input that has the highest weight. In these first 2 numbers here, the highest weight that contains a value of 1 is the third bit, and that's encoded as a 1, 0. And for the last 2 bits here, we see that the highest weight bit that has a 1 is the most significant bit, and that's encoded as 1, 1. Well, that's all for encoders today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.